Hi, our EW2 project is about ionic current measurement. Our advisor is Anshu ma'am and TA is Venkat Prashant sir. Our main motivation behind this project is flame ionization detector. Now, what happens in flame ionization detector? In flame ionization detector, we'll be having two electrodes and there will be a gas between the two electrodes. Now, we burn the gas between the two electrodes. When we burn the gas between two electrodes, the gas present will dissociate it into its cation and anion and they move towards their respective electrodes. Now, we apply a very high potential between those two electrodes so that the current is flown, but the current flown is very much small. So we want to convert that small current into a readable voltage in order to measure that current. And the current will depend on the gas and the concentration of the gas. We refer to some papers based on the project and the summary of them is as follows. We found that the range of the current detected by the flame ionization detector is in the range of 10 to the power minus 12 to 10 to the power minus 6 amperes, basically from picoamperes to microamperes. And in FID, it's the process basically happens is the ionization of organic compounds, and the ions produced in the flame are collected on the electrodes, like discussed in the earlier slide. What FID basically does is the amplify that current. This from this graph we can observe that the current depends on the gas. See, for isobutane, ethane, and methane, we are observing different currents, and for different concentrations, we are observing different currents. As concentration is more, there will be more ions and current will be more. As concentration less, there will be less ions and the current will be less. Ionization detectors are used to detect volatile organic compounds. As we have seen, for different compounds, the current we observe is different. So from that we can detect various organic compounds. And for the flame to burn, we need to supply 10% of the oxygen, which also helps in the ionization of organic compounds. Our preliminary design for the circuit to measure small currents is as follows. First, we have transimpedance amplifier. What basically transimpedance amplifier does is it converts the current into voltage and then amplify that voltage. And logarithmic amplifier, the characteristics of this will be in logarithmic fashion. And non-inverting amplifier, what it basically does is it just amplifies the voltage. Calculations for transimpedance amplifier stage are as follows. Like the old voltage here is basically current into resistance. Vin is equals to In into Rn. Now from the concept of virtual ground, we can get the voltage present here is same as the voltage here. So we assume the voltage here to be Vx and that is equals to Vin. So there, now we can basically treat it as a voltage divider circuit and we get the final voltage as Vx, the voltage present here into 1 plus Rf1 by R1, and substituting it as In into Rn, the final output after transimpedance stage voltage is In Rn into 1 plus Rf1 by R1. Calculations for logarithmic amplifier stage are as follows. Basically, first thing is the diode equation. ID equals to Is into V power Vd by neta Vt. Here ID is the current flowing through the diode and Is is the reverse saturation current of the diode and Vt is the thermal voltage of the PN junction and Vd is the voltage across the diode. From this we tried to get the value of Vd. So e power Vd by neta Vt equals to Id by Is and we have applied log on both sides. Then we get Vd equals to neta Vt into log of Id by Is. One of the main characteristics of the op-amp is no current flows into the op-amp or no current flows out of the op-amp. So the current flowing here will only pass through the diode, not through the op-amp. From the concept of virtual ground, the voltage here is 0 as this is grounded. So current flowing here is Vy1 by R3. So the current flowing through the diode is also the same Vy1 by R3. And substituting the value of id in the previous equation of Vd, we have neta Vt into log of Vy1 by R3 into Is. But the voltage here is minus Vd since the positive terminal of the diode is this thing. So as Vy2 is attached to the negative terminal of the diode, It is minus neta Vt into log of V by 1 by R3 into Is. Non-inverting amplifier, it's basically amplifier with gain 1 plus Rf2 by R2, and we have summed up all the previous calculations and the final output will be as follows.
Now coming to the reason why we use a logarithmic amplifier, we can observe that the output of the first stage is linearly dependent on the input current. However, this poses a problem as we only observe small difference in output voltage for small differences in input current. To solve this problem, we use a logarithmic amplifier since a logarithmic amplifier gives the same difference in output voltage for the same fold in increase in input current, thus allowing us to obtain a better resolution for smaller current ranges. As mentioned, we can see that the output of the logarithmic amplifier provides a greater resolution in terms of output voltage versus input current for the smaller range of input current. And then when we use a non-inverting amplifier as the third stage, we further increase the observed output voltage 11 times, thus giving us even better resolution. This is the physical circuit implemented as shown according to the previous layouts consisting of the three stages, the transimpedance amplifier, logarithmic amplifier, and the non-inverting amplifier. The circuit parameters chosen are as follows. We designed the circuit to have a maximum input current of 1 milliampere. Since the gain we have chosen is 11 and we desire the maximum output voltage of the first stage to be 5.5 volts, thus correspondingly Rn will be the maximum desired output voltage divided by the gain multiplied by the current, which turns out to be 0.5 kilo. This is the final output voltage of the third stage of the physical circuit. Since we cannot give current directly as an input, we chose to give the corresponding input voltage obtained by multiplying the current with the input resistor. Since we chose the maximum input current to be 1 milliampere and the input resistor to be 0.5 kilo ohm, we get the maximum possible input voltage to be 0.5 volts. Thus, we choose a sinusoidal wave of 500 millivolts peak to peak and give it an offset of 250 millivolts to ensure that the input ranges from 0 volts to 500 millivolts. Correspondingly, the green wave shows us the output of the final stage. This is the transfer characteristics of the circuit observed by using the acquire function of the oscilloscope. The input voltage ranges from 0 volts to 0.5 volts, which corresponds to an input current of 0 amperes to 1 milliampere, and thus we can observe a logarithmic output in terms of output voltage. This is the frequency response analysis of the circuit. We observe a 3 dB drop in output at 15 kilohertz range. Thus, from 0 kilohertz to 15 kilohertz, we observe the output to be as expected, following which there is a high attenuation due to which the reading of the oscilloscope cannot accurately measure the output voltage, giving us these high fluctuations. The slew rate of the circuit can be observed as follows. We give a pulse wave as input, according to which the corresponding output is as follows in the green wave. Thus, using this, we can calculate the slew rate. Challenges faced. The primary issue lies in which the lowest input current can be given to the circuit. General purpose op amps such as the US741 have an input bias current of around 80 nanoamperes. This means the circuit shows its desired characteristics only above this input current range, and hence this limits the lowest input current to be the input bias current of the chosen op amp. Ideally, when the input current is 0, we expect 0 volts to be the input to the circuit. However, we can see that 0 volts is the input to the circuit when the current input is approximately 80 nanoamperes, which is the input bias current of the chosen op amp. Below this current, we see that the input voltage goes into negative range, which affects the performance of later circuits. Here are various characteristics of different op amps, such as their input bias currents. When we conduct LT-SPICE simulations using OPA2182, we observe that the input voltage is 0 volts at 50 picoamperes, which is the input bias current of OPA2182, as seen in the previous slide. Thus, we can see that the final output using OPA2182 as op amp is as follows. This allows us to reduce our lower input range to 100 picoampere from 100 nanoampere, which was the lowest input range possible when using US741. Another challenge we faced on LT-SPICE was that most of the op-amps are designed by the two major companies, Texas Instruments or Analog Devices. When using symbols imported of op-amps made by Texas Instruments, we were able to observe the characteristics to be matching that of their corresponding data sheet. However, since LT-SPICE was made by Analog Devices, we observed that the op-amps were inbuilt in LT-SPICE. However, they showed ideal characteristics which did not match the corresponding values shown in the analog devices datasheets. Another challenge faced is in terms of resolution. The maximum possible voltage of supply that can be given to the circuit depends on how much voltage can be supplied to the circuit itself and the maximum supply voltage mentioned in the data sheet of the chosen op amp. For our circuit, the maximum output of the op amp cannot cross 12 volts in either positive or negative voltage since that is the chosen supply. This limits our resolution, which in turn affects the performance of our circuit. Concluding, we determined that while working with lower ranges of input of current, the op amp chosen to be used in the circuit must be selected carefully by observing its corresponding input bias mentioned in its data sheet, since below this input bias current, the circuit will not function as per the desired characteristics. Here are some of the papers and textbooks we referred while working on our project. Thank you.
Thank you.